Hi, I'm Herb Gross, and welcome to lecture number 33 in our series Gateways to Algebra, where today we tackle the awesome quadratic formula. Now, it's a formula that if you want to memorize it, it's basically has really no redeeming features to it. It's something that if you're away from it for a little while, you're going to forget it. And if you use it a lot, you'll just remember it the same way as you remember the alphabet. But the thing I want to do today is to show you another example of how in math, if we're going to do the same basic operation over and over and over and over again, rather than go through every single step again and again and again, we try to come up with what we could call a symbolic recipe that takes care of something no matter what the situation is. So to lead into where the quadratic formula comes from, let's look again at completing the square and seeing what happens over here. Suppose we have the equation x squared plus 6x equals 15. Okay? The technique for completing the square is we take what? We take half of the coefficient of x, so half of 6 is 3. We square that, it gives us 9. So we add 9 to both sides. The purpose for adding 9 here is that makes x squared plus 6x plus 9 into a perfect square. And in fact, what's it the perfect square of? It's the perfect square of the x and the square root of 9. So x plus 3 squared is 24. The next step is you take the square root of both sides. So x plus 3 is plus or minus the square root of 24. The next step is you subtract 3 from both sides. So x is negative 3 plus or minus the square root of 24. And how you want to simplify this is pretty much up to you. But at this stage of the game, we're content with getting the answer like this. By the way, it is very important when you complete the square to remember that you only take half of the coefficient of x once the coefficient of x squared is 1. You have to be careful that way. For example, suppose the problem was 2x squared plus 12x equals 40. The first thing you would do over here is to say, look, I want the coefficient of x squared to be 1. Since there's a 2 over here, that means I want to divide by 2, which is the same as saying I want to multiply by 1/2. But if you can't just multiply one part of an equation by 1/2, you have to do what? Multiply the whole equation. In other words, I have to multiply the whole left side by 1/2, the whole right side by 1/2. So if I do that, the 1/2 times 2x, the 1/2 and the 2 cancel, gives me x squared. The 1/2 times the 12x gives me 6x. And now I'm down to what? X squared plus 6x equals 20. Now I can complete the square the usual way. See, now that there's a 1 over here, all I say is what? I want half the coefficient of x. Half of 6 is still 3. Square that gives me 9. But if I add 9 to one side, I have to add 9 to the other side. Now I have what? X squared plus 6x plus 9 is 29. But the whole purpose for adding on the 9 was to make x squared plus 6x plus 9 into a perfect square, which is what? X plus 3 squared equals 29. Now take the square root of both sides. That leaves x plus 3 on the left and plus or minus the square root of 29 on the right. Then subtract 3 from both sides, so x is equal to negative 3 plus or minus the square root of 29. Now, let's take a minute to reflect. What did we just do? What we said was, look, if we have a typical quadratic equation, we look at the multiplier of x squared. If that's 1, we're in good shape. If it's not 1, we divide the whole equation by that. Then what do? We take half the coefficient of x, square that, and that's called completing the square. Well, see, now what we're going to do is instead of saying the coefficient of x is 1, or it's 2, or it's 7, we're just going to call the coefficient of x squared a, the coefficient of x b, and the constant term c, and we're going to assume that we wrote the quadratic equation in the form that we have what? An x squared term, an x term, a constant term, and at the right-hand side is 0, just for the standard form. In other words, this is called the standard form of a quadratic equation. Let me just see if I can separate the pages here. See, so what do we have? We have ax squared plus bx plus c equals 0. And a, b, and c are arbitrary constants. In other words, a can be any number, b can be any number, c can be any number. Actually, let me be a little bit more careful. We're going to assume that a is not 0, because if a was 0, we'd be back to having a linear equation. Now, what do we say next? Let's make sure the coefficient of x squared is 1. Well, if a is not 0, that means its reciprocal exists. In other words, what can we do over here? To divide by a is the same as multiplying by 1 over a. So what we're going to do is, here's what we're going to do. We'll first try to get everything that we need on one side of the equation and what we don't want to look at right now on the other side. So what I'm going to do is, I'm first going to subtract c from both sides of this equation, or add negative c onto both sides, so that I wind up with the ax squared plus bx here equals negative c. Now I'm going to multiply both sides of this equation by 1 over a. Why am I doing that? Because I want to make the coefficient of x squared equal to 1. You see, the 1 over a times a is going to give me 1. So that gives me x squared. Now 1 over a times b is what? Multiplying by 1 over a is the same as dividing by a. That's b over a times x. And then the 1 over a times negative c is negative c over a. See, the price we're paying over here is that because b and a generically name numbers and they're not specific, we can simplify this. For example, if b had been 6 and a had been 2, b over a just would have been 3. But since we don't know what b and a are, we have to leave this in what I like to call the scariest form because it's very symbolic. Now, how did we find, once this coefficient here is 1, how did we find what to add on to both sides? We took half of the multiplier of x, half of the coefficient of x. How do you take half of a fraction? To take half, see, to multiply by a half means the same as to divide by 2. All you have to do to take half of a fraction is to put 2 as a factor into the denominator. See, half of b over a is b over 2a. And what happens if I square b over 2a? Well, we'll just write it symbolically now as b over 2a all squared. But if I add b over 2a squared to one side, I also have to do what? Add b over 2a squared to the other side. So what I have right now is, what I'm going to do is what? The left-hand side has just become x plus b over 2a squared. The right-hand side, see, how do you square b over 2a? b times b is b squared. 2a times 2a is 4a squared. So the right-hand side is now b squared over 4a squared minus c over a. These are algebraic fractions. You can't add or subtract fractions until you have a common denominator. What do you have to multiply a by to get 4a squared? Well, the a has to be multiplied by a to give me a squared. Then a squared has to be multiplied by 4 to give me 4a squared. So I have to multiply the denominator by 4a to make this 4a squared. If I multiply downstairs by 4a, I also have to multiply upstairs by 4a. What does that give me? It gives me b squared over here. It gives me, see, what do I have over here? I have b squared over 4a squared. And what am I subtracting? 4ac over 4a squared. See, a times 4 times a is 4a squared. But since I have a common denominator, how do I subtract? I keep the common denominator and subtract the two numerators. So the right-hand side now becomes b squared minus 4ac over 4a squared. What do I do now? See, this is symbolic, but I do exactly the same steps. To get rid of squaring, I take the square root. If I take the square root of the left-hand side, that leaves me with x plus b over 2a. If I take the square root of the right-hand side, it leaves me with plus or minus the square root of b squared minus 4ac over 4a squared. By the way, the square root of 4a squared, isn't 4a squared 2a times 2a? That means I can take this out. So in other words, this is the square root of b squared minus 4ac over the square root of 4a squared, but the square root of 4a squared is just 2a. And what that means is I can rewrite this as x plus b over 2a equals plus or minus the square root of b squared minus 4ac over 2a. Then to get x by itself, I'm going to add negative b over 2a to both sides. And when I do that, I notice I have a common denominator here. Hence, I can keep the common denominator, combine the numerators, and what I've shown is what? That if ax squared plus bx plus c equals 0, then what must x equal? X is negative b plus or minus the square root of b squared minus 4ac all over 2a. And what this does for me is symbolically, this may look like a mess. Let's just pause for a second and think of what we've done. You see, this may look like a mess, but once you accept that formula, even write it on your cuff if you want to so that you can use it all the time. I mean, I don't care how you remember this thing. The important thing says what? Instead of going through completing the square every single time you have a quadratic equation, If the quadratic equation is written in the standard form, ax squared plus bx plus c equals 0, there's a quick way of writing down both roots. Namely, x is what? Negative b plus or minus the square root of b squared minus 4ac over 2a. I rattled that right off because I've been using it for about 50 years. I've used it a lot. I've gotten used to it. When I first learned it, I had to look it up. And in fact, when I forgot the quadratic formula, rather than take a 0 on the test, I solved all the problems by doing what? Completing the square. In effect, I was rederiving the quadratic formula every time I was completing the square. So all this means is what? It's a quick technique for replacing learning how to complete the square, or if you do know how to complete the square, it's a quicker way of getting to the result. But intellectually, it's just a symbolic way of representing the completing the square method. So let's see if we can work this thing out. Let me give you an example over here. Again, we'll try this out by something we already know. By way of review, what we've just shown is that if ax squared plus bx plus c equals 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Let's take a problem like x squared plus 5x plus 6 equals 0 and solve this in the easiest possible way. We don't even need completing the square here. We're looking for two numbers which when multiplied together give me 6, when added together give me 5. It doesn't take me long to discover that I'm looking for 3 and 2. So this becomes x plus 3 times x plus 2 is 0. Now again, if the product is 0, one of the factors must be 0. So if x plus 3 is 0, x is negative 3. And if x plus 2 is 0, then x is negative 2. So these are the two solutions. Let me show you how completing the square would work here. I'm sorry, how the quadratic formula would work here. Remember, a generically names the coefficient of x squared, b names the coefficient of x, and c names the constant term. So in this problem, a is 1, b is 5, and c is 6. Well, if b is 5, what's the opposite of b? Well, if b is 5, the opposite of b is negative 5. What's b squared? It's 25. What's 4ac? Well, if a is 1 and c is 6, a times c is 6, so 4ac is 24. So what am I going to do over here? Negative b gets replaced by negative 5. Here's the plus or minus. What does b squared minus 4ac become? b squared is 25. 4ac is 24. b squared minus 4ac, therefore, is 25 minus 24, which is 1. Okay? So that's 1 in here. And the whole thing is over 2a, but if a is 1, 2a is 2. So what's the answer to this problem? It's negative 5 plus or minus the square root of 1. Well, the square root of 1 is just 1 over 2. If we take the plus sign, negative 5 plus 1 is negative 4 over 2 is negative 2. If we take the minus sign, negative 5 minus 1 is negative 6 over 2 gives me negative 3. And there's the answer to the problem. Now, you say, okay, but why should I do the problem that way? Why should I do it that way? I could do it easier by factoring. Great. Do it easier by factoring. But now what happens if I pick one that doesn't factor? See, let's pick one like this. So let's look at 2x squared plus 3x minus 4 equals 0. By the way, notice in our formula, it's ax squared plus bx plus c equals 0. So rewrite this so that there are all additions. See, it's 2x squared plus 3x plus negative 4 equals 0. Now remember, a, b, and c still generically name what? The coefficients respectively of x squared, x, and negative 4. So in this problem, what happens? A is 2, b is 3, and this is crucial. C is not 4, it's negative 4. And now we just start filling in for the formula. If b is 3, negative b, the opposite of b, is negative 3. b squared will be 9. If a is 2 and c is negative 4, a times c will be negative 8. So 4ac will be negative 32. So what's b squared minus 4ac? b squared is 9 minus negative 32. To subtract negative 32 is the same as adding 32. So b squared minus 4ac is 9 plus 32, which is 41. So now what does x become? X is negative b, which is negative 3, plus or minus the square root of b squared minus 4ac, which is 41, over 2a. A is now 2, so 2a is 4. And by the way, this is the exact answer written this way. The problem is most of us want a numerical approximation, so what we're going to do is approximate the square root of 41 as a decimal, and I'm not going to do this too heavily right now. I just want to make a point here. I'm going to replace the square root of 41 by 6.4. That's pretty close. So this would be what? Negative 3 plus or minus 6.4 over 4. If I take the plus sign, I get negative 3 plus 6.4 over 4. That's 3.4 over 4, or 0.85. And if I take the negative sign, I get negative 9.4 over 4, which is negative 2.35. I won't check both of these, but let me check the 0.85. See, what I'm going to do is I'm going to replace x by 0.85 here. I'm going to replace x by 0.85 here. So you see what's going to happen? I'm going to have 2 times 0.85 squared plus 3 times 0.85 minus 4. And if I did right, what should if this were exactly correct, what should the answer come out to be? It's going to be 0. Let's see how close we come. On the calculator, I can square 0.85. Okay. Multiply that by 2. That will give me 1.445. Multiply 3 by 0.85 gives me 2.55. Subtract 4 gives me 0.005. And wasn't that pretty close to the exact answer? Only off by 5 thousandths. Now, is it possible that you want an answer that's more accurate than 5 thousandths? You see, there's no such thing as the so-called free lunch in this. If you're satisfied with an approximation, we can round off. If you say, I need the exact answer, because I don't know how close I have to round off to, so I want to keep the answer exact as long as possible. See, even when you're rounding off, especially with a calculator, never round off until you get to the very last step. See, every time you round off, you're building in an error. And so each time you round off, the next step you're building upon an error. In the old days, we used to round off because it was too cumbersome to do all these steps with 8 decimal places all the time. On the calculator, it happens automatically. So when I use a calculator, I don't think about rounding off till I have to. So what we might have done instead was to leave the answer in the form negative 3 plus the square root of 41 over 4. And what I want to show you is we can still check this thing through and round off whenever we want. See, we're still going to do what? Replace x by the exact value here. So instead of 2x squared, 2 is multiplying the square of negative 3 plus the square root of 41 over 4. Then we're adding on 3 times negative 3 plus the square root of 41 over 4. Then we're subtracting 4. Well, how do we square again? To square, you multiply the numerator by itself and the denominator by itself. Well, multiplying the denominator by itself, since it's a 4, gives me a 16 down here. How do I multiply the numerator by itself? I square the negative 3, which gives me 9. I square the square root of 41. See, squaring the square root gives me back the 41. I multiply these two numbers together and double it. So negative 3 times the square root of 41 times 2 is negative 6 square roots of 41. That takes care of this term. Now I still have these terms over here. And how do you add fractions? You need a common denominator. By the way, I guess one of the things we could do over here is, since the 2 is in the numerator, see, whenever you're multiplying by 2, it's the same as if the 2 is in the numerator. The 2 here can cancel with the 16 here, leaving me with an 8. So now the 2x squared plus 3x negative 4 can be written like this. And by the way, what's my common denominator over here? It's 8. So in other words, what I want to do over here now, see, this is still equal to 0. To get rid of my common denominator, what can I do? Multiply both sides by 8. See, if I multiply this term by 8, this will drop out. The 8 multiplying the 4 in the denominator leaves me with a 2. That 2 is going to double this. This is going to become what? 6 times the square root of 41. And the negative 9 becomes negative 18. The 8 also has to multiply the negative 4. That's going to give me negative 32. Okay? And then that's going to be equal to 0, because 8 times 0 is still 0. And in fact, if you didn't want to multiply both sides by 8, you still could have done what? Use 8 as a common denominator and put the whole thing over 8. In other words, whichever way you do it, you're going to wind up with what? 9 minus 6 square roots of 41 plus 41 plus 6 square roots of 41 minus 18 minus 32 all over 8. And look what happens over here. His negative 6 square roots of 41, his positive 6 square roots of 41, that drops out. His 9 plus 41 is 50. 50 take away 18 is 32. 32 take away 32 is 0, and this checks exactly. See, there's no approximation doing it this way. And to sort of summarize what we're doing over here, let's take a look now to see when we get the two distinct roots, when we get the no roots, and when we get one real root. What we've shown in summary now is what? If we write the quadratic equation in its standard form, ax squared plus bx plus c equals 0, x will always turn out to be what? The opposite of b, plus or minus the square root of b squared minus 4ac over 2a. b squared minus 4ac is called the discriminant. And the reason it's called the discriminant is that it discriminates for us what the roots are going to look like. See, if b squared minus 4ac is a positive number, then this will be two square roots, one of which is positive, one of which is negative. That will tell us that we have two real roots to this equation. If b squared minus 4ac is negative, then we're taking the square root of a negative number, but no number times itself is negative, at least considering the numbers that we've studied so far in this course. So we would say there are no roots in this case. And if b squared minus 4ac is 0, it drops out, and x is simply what? Minus b over 2a, and there's no two roots here. In other words, you only get what? One real root. At any rate, what this does is, this completes how we're going to solve a quadratic equation once we have it. What I still want to talk about are additional ways in which we get quadratic equations. I want to talk a little bit more about graphing quadratic equations. I have a few things like this that we want to do, but that will all be done in due time as we do our future lectures. But for now, I want to just take time to reflect and have you see once again that if you don't lose sight of the forest because of the trees, completing the square was nothing more than finding a recipe for the quadratic formula was nothing more than finding a recipe generically for completing the square. Completing the square works all the time, whereas trying to find two numbers whose product is the constant term and whose sum is the coefficient of x, it always works, but they aren't always whole numbers. But the real important thing is what? That we solve quadratic equations by reducing them to a pair of linear equations. And we'll talk more about this next time. But until next time, study hard, stay young, and I'll see you soon.